Hi folks, welcome to our review for our final in Calc 2. You're going to see a series of questions, and this is the first part. It's basically your basic questions in terms of evaluating integrals, determining if an improper integral is convergent or divergent. We'll take a look at convergent or divergent series, and along with that, sequences as well. So if you have any questions along the way, please ask, and then there'll be a second part coming at a later date in terms of more application problems like finding the volume revolving around a certain axis, things like parametric polar equations as well. We'll toss into that second review. So as always, if you have any questions, please ask them along the way, but this is based upon an old exam, so you'll see a lot of questions and hopefully you've worked them out ahead of time so you can kind of follow along. So without further ado, let's get started. So you have this integral where you have an x squared and a square root of 25 minus x squared. So what sort of integration technique should we use? Well, with this square root and we have a 25 minus x squared, that's giving you a pretty good idea that this is going to be a trig substitution of some kind. So with that in mind, we can try and guess as to what's going to happen. Well, notice you have this 25 and then minus x squared. That usually is an indicator that you have 5 sine of theta as your trig substitution, and that would mean dx equals 5 cosine theta, d theta. Now, what happens if you made a wrong guess? Well, you'll notice it right away when we try and reduce this down, and I'll show you what I mean. So if you take this now, the integral becomes, we have a 5 cosine theta d theta up top. X squared would be 5 sine of theta, that quantity squared, and then we have the square root of 25 minus 5 sine theta, the quantity squared. So what does all this junk equal? Well, it boils down to, we'll have a 25 sine squared theta down below. Up top we'll have a 5 cosine theta, and then this becomes square root of 25 minus 25 sine squared theta. Now notice that this makes this integral, well, you can cross off one of the 5's up above with the 25 down below, and so we can pull out a 1/5. That might make our life a little easier. So we have cosine theta, sine squared theta, and you have a 25 in common with both those terms. So we're going to factor that out. And why would we factor that out? Well, that leaves us with a 1 minus sine squared theta. And that is one of our trig identities. If you recall, just off to the side here, you have sine squared theta plus cosine squared theta equals 1. That means cosine squared theta equals 1 minus sine squared theta. That is one of our trig identities, so we can replace what's underneath here in our root with just cosine squared theta. Okay? So keeping that in mind, that makes, when we take the square root of a cosine squared theta, yeah, granted you can have an absolute value, but we aren't going to worry about that too much. This whole thing equals 1/5 times the integral. We have cosine theta. We have a sine squared theta, and the square root of 25 is 5, so we have 5, and then we have the square root of cosine squared, we'll just say is cosine theta. Technically there's an absolute value involved there, but we won't worry about that too much. So, oh, and I need the d theta hanging out up there. So what happens now? Well, we get 1/5, or actually we can pull that other 5 out, you get 1/25, and your cosines will cancel. You're left with the integral of d theta over sine squared theta, which has a better way to be written. This is 1/25, and this is the integral. Well, that's just cosecant squared theta d theta. Okay, so that antiderivative, if you notice, that's going to be 1 over 25, and then the antiderivative of cosecant squared is negative cotangent theta plus some constant c. So using this up here, we'll draw a triangle in a second. We have x over 5 equals sine theta What does that mean? Well, that means when we draw this triangle with the theta here, the opposite side is x, the hypotenuse is 5, so that means this is square root of 25 minus x squared on that leg, just by Pythagorean theorem. Questions on that piece? So now when we go to cotangent of that theta, remember cotangent would be adjacent over opposite, so this is 1 over 25, negative, and then it goes adjacent, so square root of 25 minus x squared over the opposite, which is x, plus c, and that's your final answer. Questions on that? So I don't see any questions, so we'll keep on moving along. Alright, so our next one, we have cosine squared theta, sine squared theta, d theta. Well, in this case, we have a nice identity for cosine squared theta and sine squared theta. This is 1/2 1 plus cosine of 2 theta, and sine squared theta is 1/2 1 minus cosine of 2 theta, I believe. Okay, so with that in mind, this integral is equal to 1/2 1 plus cosine of 2 theta times 1/2 1 minus cosine of 2 theta. And then we have the d theta. So this becomes, notice this is perfect squares, so 1/2 squared, by the way, we get 1/4. Then we have an integral, and so you can notice this is a plus minus, and if you recall, a plus b, a minus b equals a squared minus b squared. So this one won't be too bad, hopefully. This is 1 minus cosine squared of 2 theta. And then we want to take d theta of that. Well, cosine squared of theta equals this 1/2 1 plus cosine 2 theta. So we can break this down even further. And so we get equals, we have a 1/4 out in front. Goes 1 minus, and this would become 1/2 1 plus cosine of 2 times 2 theta, right? And then we want to take all this and put a d theta at the end of that. So this whole thing, let's simplify this a little bit more. Notice you have 1/2 sitting right here, and then plus a 1/2 cosine of 4 theta sitting right there. So we have 1/4, and we go 1 minus 1/2 makes another 1/2, plus 1/2, or I'm sorry, not plus, but minus, because I have to distribute that minus sign to each of those. So minus 1/2 cosine of 4 theta. And we have d theta. Notice both of those have a factor of 1/2, so we can pull that 1/2 out, and we now have 1/8 the integral of 1 minus cosine of 4 theta. And then we have a d theta. Okay, so moving forward from there, what happens? Well, this one we are going to use a u substitution. You get u equals 4 theta, then du equals 4 d theta, or d theta equals du over 4. Right? And in that case, notice what it'll do. It'll multiply whatever you have in here by a 1/4. But at the end of the day, the antiderivative of 1 isn't bad. That's 1/8 theta minus, well, here, let me put parentheses around all this. So now, when we go cosine of 4 theta, the antiderivative of that is positive sine. So this would be sine of essentially 4 theta. And where that comes from, just real quick, this would become cosine of u, and then du over 4. So you can pull out the 1/4, so you get 1/4 integral cosine of u. Notice that makes sine of u, but we'll have a 1/4 as a factor out here. So we'll have 1/4 sine of 4 theta, and then we'll have plus some constant c. So if we write all this out, it's going to be 1/8 theta minus 1/32 sine of 4 theta plus some constant c. And we're done. So now let's take a look at the next one, see what happens. So now we got something that looks like partial fractions in this case. And why can we say this is going to be a partial fractions? Well, notice first off the integral is defined over this interval, 2 to 3. So we can go 2 to 3, but we can write this as 1 over x squared minus 1 factors to x minus 1, x plus 1, and then we have a dx. So now we just need to find constants in using partial fractions decomposition. So you have a over x minus 1 plus b over x plus 1 equals 1 over x minus 1, x plus 1. So what we'll do is multiply both sides of equation by x minus 1, x plus 1. This will give us a chance to solve this thing. So notice the x minus 1s would cancel in that first one, and you're left with a times the quantity x plus 1. Plus in the second case, you'd have b times the quantity x minus 1 equals, and then the two terms would cancel in the denominator of that last piece, and you get 1. So notice we can solve these things just plugging in certain x values. When x equals -1, notice what do we have? Well, we'd have a times 0, so a times 0 plus b times -1 minus 1 is -2 equals 1. So what does that do? Well, that implies, well, the a disappears and you get b equals -1/2. So you're done with that part. When x equals +1, you get a times 2 plus b times 0 equals 1. And that implies that a equals +1/2. So our integral of 2 to 3 of 1 over x squared minus 1 dx is the same thing as the integral from 2 to 3 of, well, it goes, remember, the a over x minus 1, so we have 1/2 over x minus 1 minus, our other case would be -1/2, so that's where we get minus out in front, 1/2, and then this is x plus 1. And this goes dx. So luckily we can pull 1/2 out in front of the whole thing. So you get 1/2 times the integral from 2 to 3 of 1 over x minus 1 minus 1 over x plus 1. Since both of those happen to be the same. That doesn't always happen, but in this case we kind of lucked out. So what does that mean? It means we get 1/2 the natural log of x minus 1 minus the natural log of x plus 1. Evaluated at 2 and 3. Okay, so now we just plug in 2, we plug in 3, and we're done. So we get 1/2. When we plug in 3, you get natural log of 3 minus 1 minus natural log of 2 plus 1, or 3 plus 1. My apologies there. It should be a parentheses. Hold on one second there. Parentheses. And then so now we can take this and subtract off. We want to do natural log of 2 minus 1 minus the natural log of 2 plus 1. Well, that part's natural log of 1, which is 0. This part is natural log of 3. this part is natural log of 2, and this part is natural log of 4. Okay, so what do we have? We have natural log of 2, oh, and we have a 1/2 out in front. 1/2 natural log of 2 plus a natural log of 3, because a minus and a minus makes a plus, plus natural log of 3 minus a natural log of 4. Now if you want to get fancy with this, we can. And what can we do? We can combine these. So you combine these two into a single logarithm. This becomes natural log of 6 because you multiply those. And so then you can combine these two pieces, and this becomes the natural log of 6 over 4, which is the natural log of 3/2. So this is 1/2 natural log of 3/2, and you're done. And we could have been done before that, but just let you see what our exact answer becomes in that case. Okay, so we've seen a few of them, a few different methods. We've seen trig substitution, trig integrals. Now it's kind of, well, let's work another partial fraction like we just did, but something slightly different. So why is this different? Well, we are going to have to divide. So x cubed plus x divided into x cubed plus x plus 1. Luckily, and so actually I should be careful here. Some of you might see right away what your remainder is going to be, but just in case you don't. So we'll put the 0x squared in there. But notice this is x cubed plus 0x squared plus x is what we can write down below. Okay. Well, notice this goes in here once. Excuse me. And so when we subtract these two things, we're going to get x cubed plus 0x squared plus x. And so notice that makes 0 for everything. It just cancels out. And so we drop down the plus 1. And so notice that goes in. So, oh, I'm sorry. I put in the 1, but so notice that means this 1, this can't divide in here anymore. This is our remainder. So what does that tell us? Well, it tells us that this integral can be rewritten as 1 plus 1 over x cubed plus x. And then we take that and we do a dx. Right? And so this integral becomes 1 plus 1 over, we can factor out an x. This is x times x squared plus 1. And then we have a dx sitting right there. Okay. So that means our partial fraction decomposition becomes a over x plus bx plus c over x squared plus 1. And that should equal 1 over x in x squared plus 1. Okay, now moving forward from there, we can multiply both sides by x times x squared plus 1. So notice what you get is a and then x squared plus 1. Plus, let's see here, this would be bx plus c all times x. Okay, and that should all equal 1 in this case. Questions on that? So now we can kind of move forward here. When x equals 0, what do we get? Well, we get, notice the second part, you'd have 0 times bx plus c, so that makes that whole thing 0. So you get a times 1 plus b times 0 plus c times 0, as I mentioned before, and then that equals 1. So what this means then is that a equals 1. Okay, well from there, so now let's say a equals 1. Notice you get x squared plus 1 plus b, and let's write this as bx squared plus cx, so give you a slightly different way to look at this, equals 1. So notice you can subtract the x squared plus 1 over on the other side. So what happens? Well, we're left with the ones would cancel, so you're left with 0. So we have bx squared plus cx equals negative x squared. So that implies that b equals negative 1 and c has to equal 0. Okay, so now our integral becomes the integral of 1 plus, okay, so we have a over x, so that's 1 over x. Well, that isn't going to be too bad. And then minus, so we have no c value, so it's just the bx, so minus 1 x over x squared plus 1. And then we have a dx. So some of this is really nice in terms of our antiderivatives. So we have x plus the antiderivative of 1 over x is natural log of x. And then minus, let me put that integral again, and we'll have x over x squared plus 1 dx. And notice that'll bring a constant c in there. So, but we'll have u equal to x squared plus 1 in that, and then that means du equals 2x dx. If you don't remember all this stuff, so you get du over 2 equals x dx. And if you look, that means that this integral x over x squared plus 1 dx is the same thing as the integral of, we have an x, we have a dx there, so that would be a du over 2 over just u. So that means we can pull out the 1/2. We get 1/2 1 over u du, which is 1/2 natural log of the absolute value of u, plus some constant c. And so this thing is just 1/2 natural log of x squared plus 1 plus some constant c. So this thing equals, and I should put equal signs all the way through here, x plus natural log of the absolute value of x minus, because we have a minus out in front, 1/2 natural log of the absolute value of x squared plus 1, although that's always positive, so we don't need the absolute value in this case, and then plus some constant c. And we have our antiderivative. Okay, so there's the integration. You've seen how those work and how we can break those things down. Remember your u substitutions and things like that. So all those pop up over and over again. Now when we try and determine if an integral is convergent or divergent, we have a few more things at our disposal. What do we mean by that? Now notice our intervals from 1 to infinity. So first off, if we compare 3 plus x to the 12th and just x to the 12th, which one's larger? Well, hopefully you recognize this on the interval 1 to infinity, right? So we can kind of move forward from here. So that means if we go 1 over 3 plus x to the 12th, and notice I put greater than or equal to, that's not necessary. I could just leave it greater than, that would do the trick, but there's no harm in putting that extra equal to symbol there. So we would have that this holds on the interval 1 to infinity. So that means, before I do that, what I could say as well, if I take a 4th root here, and I take a 4th root here, that means I can take a 4th root here, and take a 4th root here. And notice that matches a little bit better, right? Now let's toss an x up top. So you have x, and then 3 plus x to the 12th, where we have a 4th root involved here. And that's less than or equal to x, and then we have a 4th root of x to the 12th. That holds on 1 to infinity. So moving forward from this spot, though, remember, x, if I multiply by cosine squared x, the maximum that could be is 1, so this thing is larger than this integral. So you have this over the 4th root of 3 plus x to the 12th. So now, let's take a look at the integral from 1 to infinity of x over the 4th root of x to the 12th dx. Well, notice another way to write that is the limit as t approaches infinity, the integral from 1 to t, and this is x over, well, the 4th root of x to the 12th is just x cubed. So another way for us to have written that is just the limit as t approaches infinity of 1 to t of 1 over x squared dx. Well, that's convenient, because now what that allows us to do, we can take that antiderivative, we get the limit as t approaches infinity of negative 1 over x and evaluate at 1 and t. So this thing equals the limit as t approaches infinity. You get negative 1 over t, minus and minus makes a plus 1 over 1. And so that should equal, well, notice this whole thing goes to 0. So that thing equals 1. So what does that tell us about this integral? Well, this thing converges by the comparison theorem since we have x cosine squared x 4th root of 3 plus x to the 12th is less than or equal to, well, we found it's less than or equal to 1 over x squared on the interval 1 to infinity, and the integral from 1 to infinity of 1 over x squared dx equals 1. Right. So we have this thing's converging by comparison theorem. Notice, not even touching the integral. That's the nice part here. So we can get away without working around that integral and get an answer. Otherwise, that would be actually quite difficult to do. So on the other end of the spectrum, we'll go ahead and evaluate this integral. So you can always manipulate it if need be, but this one's a nice integration by parts. So you have a limit as t approaches negative infinity. Oops, that's negative infinity. And so you go from t to 0 of x e to the x dx. And so this is integration by parts. It's the one we've been missing in terms of our integrals in the get-go. So that's why I kind of had this here so we can test it in other places. So you get u equals, and then you have a dv equals. So u, we usually want to drop the derivative down a power. So that's why we'll put u equal to x. That means du equals just dx. And if dv equals e to the x, that means v equals e to the x. And remember, you're looking at, it goes uv minus the integral of v du is what that becomes. So this thing equals the limit as t approaches negative infinity of, well, uv, so that's x e to the x, evaluated at t and 0. Okay, and then it goes minus the integral from t to 0 of, oops, and we have e to the x dx. So if we're to evaluate this the whole way, we can move the t interval from t to 0 a little bit later on down the road, because the antiderivative of e to the x is just e to the x. So this becomes limit as t approaches negative infinity of x e to the x minus just e to the x, evaluated at t and 0. So now this becomes a limit problem. This is the limit as t approaches negative infinity. Okay. And what do we have? Well, we have x e to the x. Oops, sorry, I don't need the x anymore. I can plug in 0. So you can go 0 times e to the 0 minus t times e to the t minus, and then in the other case we'll have e to the 0 and then minus e to the t. Well, the easiest couple of the bunch here, so this one obviously is 0, but this one's also Oh, and let me put that other parentheses. As t approaches negative infinity, this thing goes to 0. So really the big questions are this t e to the t and that negative e to the 0. Well, e to the 0 is going to be 1. So we have to write this a different way for that t e to the t. So limit as t approaches negative infinity. Let's write this as e to the t. Well, let's see here real quick. Let's write this as t over, and then be 1 over e to the t, which is just e to the negative t. Okay, and let's see what happens here. And then we'll have a minus 1 at the end of the day. And so we can use, now we have, if you notice, you get negative infinity over e to the infinity, which is infinity. So you can use L'Hopital's rule. So that becomes limit as t approaches negative infinity. Derivative of the numerator is just 1. Derivative of the denominator is negative e to the negative t. Right? So if you actually move that back up top to where it belongs, well, actually that's not even necessary. You can plug in an infinity, a negative infinity, that becomes e to the positive infinity, which you get infinity down below, negative infinity down below. That's 1 over something that's approaching a very large negative, I guess you could say. And so that would be 0. So this becomes 0 minus 1. So our answer is negative 1. So this thing is convergent, because we actually found the value. Okay. So now moving from those integrals, let's try and hop into series and see what happens. So this first one's actually really tricky, because you might think, okay, ratio test, root test, those are the natural go-tos for a lot of people. But in this case, those won't work. So we have to use something else, but it's not an alternating series completely, because you're going 3, then 6, sine of 3, sine of 6, sine of 9, sine of 12. That thing's bouncing all over the place. But there is a fix. Notice that this is larger than 0 if we take the absolute value. Okay? But if you look at that, what happens? Well, you can think of 1 is larger than the maximum value sine can take. So if you went something like this, you would have 1 over 1 plus the 1 plus 4 to the n. That's going to be larger than the sine of 3n over 1 plus 4 to the n. But now, notice if we're starting with a number down below, the larger the number down below, the smaller this thing is getting. So if you compare that to 1 over 4 to the n, notice this denominator is larger on the left-hand side of this inequality. So the 4 to the n would actually be better in our scenario. So we have this nice inequality working all the way throughout. So this thing happens on the interval 1 to infinity. Why is that so important? Well, we know that the summation n equals 1 to infinity of 1 over 4 to the n is a geometric series with r equal to 1/4. So it is convergent. So that happens, then that means the summation n equals 1 to infinity of the absolute value of sine of 3n over 1 plus 4 to the n is convergent by the comparison theorem. But that doesn't match exactly what we're looking for, or by the comparison test, I should say. Okay? So, but there is something else that we know. Since we're looking at the absolute value of all the terms, we know that this thing is called absolutely convergence. So since that series is absolutely convergent, there's a result that says it must also be convergent. So there's a few pieces we had to put together, but as soon as you recognize, you can look at the absolute value. That takes care of it using comparison theorem, and we're done. Right? It would have been a lot harder if we had the absolute value diverges, because then that doesn't tell us anything about the original summation. But since it converged, we have comparison test right away, and we're done. Okay, that's quite important in terms of how to work it. Now in this next one, we do have an alternating series, so to make our life simpler, let's just use the alternating series test. And you can actually go back and check, is this thing going to be absolutely convergent just for kicks if you want, but alternating series test will do the trick. The easier of the two things to test usually is the limit as n goes to infinity of just the positive terms. So you can get rid of the -1 to the n. Well, notice that's going to be, well, you can use L'Hopital's rule if need be, if you don't see it right away. But so notice that would be 1 over 8n, and so this thing equals 0. So that's a check on that part. Now we need to show decreasing. So first off, let's go f of x equals, and we'll need to show decreasing on the interval 1 to infinity, or some positive constant to infinity. So in this case, we'll say f of x equals x over 4x squared plus 1. So how do we show decreasing? Well, we take the derivative. And so what happens here? Well, we get, this is 4x squared plus 1, the quantity squared. That means we take the 4x squared plus 1, drop it up top. Derivative of the top is just 1 minus, and then we have the top, so the numerator times the derivative of the bottom. So the derivative of the bottom would be 8x. So notice if we simplify this thing, we're going to get 4x squared plus 1 minus 8x squared. Well, that makes 1 minus 4x squared up top over 4x squared plus 1, the quantity squared. Well, notice if you plug any number 1 or higher, we have that this means we have a decreasing, so f of x is decreasing on the interval 1 to infinity. So we have it's decreasing. We have it, the limit as n goes to infinity goes to 0 of the terms, and so this means by the alternating series test that this little shindig so converges by the alternating series test. Okay, so now we're rocking and rolling. Let's try another series. So this one looks kind of nasty, but it's not too bad. So let's take a look as to what happens. Well, notice you have another way to write this is the summation n equals 1 to infinity of, we could break this into 2 arctan of e to the n, the quantity squared, and then we could raise all that to the nth power. But then on top of that, we could have the 9 grouped in, and this whole thing is raised to the nth power. And that might look a little bit better because now what that screams to us is the root test. So that means we can go limit as n goes to infinity of the nth root of this 2 arctan of e to the n squared all over 9, and we want to raise that to the nth power. Well, notice in that case what's going to happen is you're going to get the n and the nth root will cancel, and you're left with the limit as n goes to infinity of 2 arctangent of e to the n, and then we're taking that and we're squaring that whole thing, and then it's all over 9. Okay, the beauty is the only place n is involved is this e to the n, right? So we can take that limit as n goes to infinity of this thing, e to the n, that means it's going to infinity. So basically this becomes of arctangent, whatever happens to that as we approach infinity. Well, luckily we know the graph of arctangent looks something like this, where you have these asymptotes. The asymptote up top is pi over 2. The asymptote down below is negative pi over 2. So notice as we go out further and further towards infinity, we're getting closer and closer to pi over 2. So this thing equals 2 times pi over 2, the quantity squared, all over 9. So notice that equals pi squared over 9. Now I don't know much, but I know pi is like 3.14, so if I square that, that's going to be larger than 9 because I have a number larger than 3 that I'm squaring. So this thing is greater than 1. So since it's greater than 1, that means that this summation, n equals 1 to infinity of 2 arctan of e to the n raised to the 2n all over 9 to the n, diverges by the root test. So the root test came through in the clutch on that one. Okay, so now we have another one. When we see factorials and there's only factorials involved, this is probably screaming ratio test to us. So just a little reminder, the limit as n goes to infinity, you want to take an plus 1 over an. How does that work? Well, okay, so this is the limit as n goes to infinity. We want to change all the n's to n plus 1s. Just make sure you put parentheses where necessary. So you get n plus 1 factorial cubed all over 3 n plus 1 factorial. And that's the numerator. And then down below we'll have n factorial cubed over 3n factorial. Taking the absolute value. Absolute value is really not necessary since everything's positive here. But we can make this limit as n goes to infinity. Now let's try and group things together. And we're going to multiply by the reciprocal of the denominator. So first things first. Let's kind of look this, and as I said, we can drop the absolute value at this point. We can write 3n factorial, but down below we're going to need a 3n plus 3 because this n plus 1 times 3 we got to distribute. So this is 3n plus 3 factorial, not 3n plus 1 factorial. So make sure you're aware of that because of that quantity there. So now on the other case, we're going to have n factorial cubed down below, but I'm going to write that a different way. I'm going to write it n factorial, n factorial, n factorial. And then up top, we can write it as n plus 1 factorial, n plus 1 factorial, and then an n plus 1 factorial. Now, why is that so important? Well, that allows us to break this down a little bit more. And so first off, we have the 3n factorial. Let's see if we can get rid of that. Well, if you start at 3n plus 3, the term before that would be just one term less, so you subtract 1 from that, you get 3n plus 2. And the term before that would be 3n plus 2 minus 1, which is 3n plus 1. And the term before that would be 3n plus 1 minus 1, which is just 3n, and then we can put a factorial. And notice your 3n factorials would cancel. Yeah, the ratio test is right. That it comes through on the clutch. So now, if we're looking on the other side of the fence, we can write this as n plus 1 times n factorial. I'll separate it into 3 separate fractions over n factorial times n plus 1 times n factorial all over n factorial again. And then we have an n plus 1 times n factorial all over n factorial one last time. So now you can see all the things canceling here. And then we have the 3n factorials there. And so now we can simplify this. Limit as n goes to infinity. And what I would do is I'd probably just group them you can do m plus 1 over 3m plus 1, or 3m plus 3. And then you could do m plus 1 over 3m plus 2. And then you could do m plus 1 over 3n plus 1. Right, since you have 3 of each in the numerator and denominator. So now, taking a look at each of those, you can use L'Hopital's rule on each one separately. And so you get 1 over 3, 1 over 3, and 1 over 3. So that you get 1 over 3 times 1 over 3 times 1 over 3. And so that ratio test did come to a rescue once again. This was 1 over 27, which is less than 1. So what does that mean? That means the summation n equals 1 to infinity of n factorial cubed over 3n factorial converges, because that number is less than 1, by the ratio test. Okay, so hopefully that makes sense in terms of how we work that one out. Now we'll break down to one more that's kind of tricky for some people. So we have this summation n equals 1 to infinity of a sub n, where the partial sums Sn are given by Sn equals n sine of 5 over 2n. What the heck does this become? Well, actually, this one's a lot easier than most people think. So, for example, what this is telling us, I'm going to rewrite with i's here. So this is the summation I equals 1 to n of the AI's would be Sn. So this thing equals A1 plus A2 plus A3 plus yada 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 all the way up to AN. Now think about this. We want to take n to infinity. So in order to do that, all we need to do to solve for this one is take the limit as n goes to infinity of these Sn's, because it's saying it's the partial sum. So this was all just a play on what does it mean to be a partial sum. So in fact, this equals the limit as n goes to infinity of n sine of 5 over 2n. But unfortunately, it's not that easy, where you have infinity times 0, so we got to do a little bit of work. Not much, but just a little bit. So another way you can write the inside, by the way, is 5 halves times 1 over n. And I'd recommend that because it'll make our lives a little easier. So we'll write this as sine of 5 halves times 1 over n. Just for the sake of when we're taking the derivative, life will be a lot easier in that case. So now when we plug in n going to infinity, you get 0 over 0, which is good. We want that, so we're in good shape now. So we can use L'Hopital's rule. Okay. So first off, we have limit as n goes to infinity. The numerator becomes cosine of 5 halves times 1 over n. But now we got to take the derivative of the inside, so that's going to be 5 halves times derivative of 1 over n is negative 1 over n squared. And luckily, down below, we have derivative of 1 over n. Well, that's just negative 1 over n squared. So our negative 1 over n squareds will cancel immediately. So this thing, and remember, we're only determining if it's convergent or divergent, but we'll actually do something much better. So we get the limit as n goes to infinity. We can pull that 5 halves out in front, and what we're left with is just cosine of, and I'll make it back into 5 over 2n. Okay, so the inside goes to 0, so this becomes 5 halves times cosine of 0, and cosine of 0 equals 1, so our answer is 5 halves. This is the actual value of this this series. So the summation n equals 1 to infinity of a sub n, since we're talking partial sums for that, you usually don't have that, just an FYI, equals 5 halves, so the series convergence. Now don't confuse that with the test for divergence, where we actually look at the inner term, the sequence inside of there. So the series in this case converges. It was the fact that we had the partial sum value that allowed us to find the answer. And that doesn't happen too often, but just an FYI, it's one of the things that we're trying to look at there. Okay, so we're going to finish this thing, bring it home with 2 sequences, and see if we can solve these. So determine whether the following sequences are convergent or divergent. So what do we have happen here? Well, all we need to do when we're determining if a sequence is convergent or divergent is take the limit as n goes to infinity. Okay, so limit as n goes to infinity, we have of natural log of n, the quantity squared over n. So what do we do here? Well, it's not too bad. We can use L'Hopital's rule because we have infinity over infinity, so we have the limit as n goes to infinity. The derivative of the numerator, it goes 2 natural log of n times the derivative of the inside, which is 1 over n. And the derivative of the denominator is just 1. So that seems hunky-dory, but you have infinity times 0, so once again we probably want to rewrite this as the limit as n goes to infinity of, now it's 2 natural log of n all over n. Okay, well, so in this case, what do we have? Well, this thing equals, we can use L'Hopital's rule once more, because we have infinity over infinity in this case. So this becomes limit as n goes to infinity of 2 times 1 over n. And we could have pulled that 2 out in front all the way if need be. N times 1. So this whole thing equals 2 times, well, the limit as n goes to infinity, this thing goes to 0, so that becomes 0 for our final answer. What does that actually tell us? So just a big picture in terms of what happens. That tells us that n is going to infinity much, much faster than the natural log of n squared. That's the big idea. And when we're taking series, so if we were to look at a series of this thing, we're trying to see how fast is this thing going to 0. Is it going so fast that the sum of all the numbers along the way actually goes to some finite number? And that's the whole picture in terms of what we're looking at in series. So notice on the last one, we're actually using series and sequences together. So it's all just a trip on words here. But we have a positive term series. That's important. If I don't put in positive term series, this becomes a different problem. So there's 2 scenarios here. Case 1. What Sn represents, so we want to take the limit as n goes to infinity of Sn, which is the same thing as a summation. Let's say k equals 1 to infinity of some a sub k. If this thing equals c, where c is a constant, then the limit as n goes to infinity of 5 to the negative Sn would equal, well, that thing's going to infinity, so this thing just becomes 5 to the negative c. So what that tells us in this case, we have something that's convergent. But that's not the only possibility. And here's where the fact that it's positive term series is important. The limit as n goes to infinity of Sn equals this summation. But notice, so sometimes you can have series that oscillate up and down, up and down. So -1, +1, -1, +1. In those cases, you don't know, it diverges, but you don't know where it diverges to. However, if we're always adding a positive number and this thing's to diverge, where must it go? Well, it has to go to infinity. Okay, 3e and 4b. Okay, so the question is, I am confused with the wording of 3e and 4b. How are they asking something different? Okay, and so I'm assuming 3e is referring to this one. So let's take a look here. If you look at this, the Sn, if you notice, we're talking about a series, right? So the series is what we're trying to see converges, right? So the series that we're looking at, we're given these partial sums, which forms the sequence, right? So you're starting with a series, you're converting the series to a sequence, and then you're determining what value that is, and then we determine the series converges. In the second case, we're starting with a sequence, but the sequence is made up of terms that involve a series, right? So that's the big difference, is the Sn is up in the exponent in a sequence. So we're doing a couple things all at once here. So with this, the fact that we have these two cases to consider, that can make a big difference. But luckily, if you look at the two cases, the fact that the second one is either some constant or it's infinity, right? That doesn't happen if you have an alternating series of some sort, or just a series that can go positive and negative at any points in time. This does not work, right? So I just want to make sure on that. I'm glad that's all okay, so we're good. But yeah, I just want to try and hit that home, because this is tricky. It's all in the wording, really. So in what happens, if this is infinity, you get the limit as n goes to infinity of 5 to the negative Sn. Well, that thing is going to negative infinity now up top. Well, that means that this whole thing goes to 0. Yeah, that's the whole trick to all these. It's just the wording on a few of these, right, where you have the SNs and things like that. What's a partial sum? What's a sequence? So the sequence is this A sub k, that forms a sequence as well, right? The S sub n just form a sequence of they're basically forming a sequence of all these partial sums. So yeah, it's a ton confusing at first, but that's why I wanted to toss it your way so you could see that and how it works out. But in either case, these are convergent. So the fact that you have a positive term series, this whole thing converges. Now, we don't know if it converges to 5 to the negative c, or another way, you could write that as 1 over 5 to the c, or it could converge to 0, right? So either one, you're going to get something convergent. Okay, so that's it for today's lesson. Next time, as I mentioned, we'll talk about volume a lot more. Volume, we'll get into that. We'll get into parametric polar curves and calculating some areas there and things along those lines. So we'll see more next time. I'm planning on having that in a couple of days. So, are there any more questions in terms of this stuff? This is the bulk of what you'll see come final time. Okay, so there'll be a few more questions involved with, as I mentioned before. So yeah, I don't have the exact date, but it'll either be in 2 days, so Wednesday or Thursday, one or the other, for the next review. So I'll let you know as soon as I get that taken care of. Okay. All right. Hope you all have a good night, and I will see you next time.